Testing, 1, 2, 1, 2, testing. How's everyone doing tonight? Can everyone hear me okay? Good. Seeing lots of yeses in the chat. Go ahead. If you haven't already, say hello in the chat. Let me know you found it. You should be looking for something that says either Zoom group chat or zoom.us, something to that effect. Go ahead, say hello. Let us all know that you're here. I'm showing a total of 23 participants so far. Good. Hello, hello. All right, as you guys know, I'm really big on participation. So if you guys don't already have your calculator, now's a great time to get it. I'll be asking questions throughout tonight's session, and I'll be relying on you guys to help me solve and to check my work. I encourage everyone to participate. If you haven't participated in the past, now's a great time to join the fun. Participating really helps you to retain the information, and it really helps with the learning process in general. So today is just about T-minus 2 weeks away from the April PE exam. So what we have in store for tonight, tonight's agenda is we're going to talk about really quick, what should we focus on this close to the exam? I had actually more than one of you asked for either a pep talk or just kind of we'll call it a refocusing talk, but we'll touch on that briefly. We want to make sure no one's wasting their time or focusing on things that might be a little counterproductive up until this point, and maybe a couple of things that we want to take a break and start focusing on now before we get to the exam. So that'll be first. Next, gotten a lot of emails lately on the 2-watt meter method. So we'll go over that. There was actually some good discussion on the discussion page, and I actually updated a few of the formulas. So if you haven't seen that, I would definitely go back to that. But on today's example, we're actually going to draw out the watt meter, show where those formulas come from, and then we'll pick a couple of values at random and do an actual live example. Next, been getting a lot of emails on power electronics. So the full wave bridge diode rectifier is one of the most common ones that we'll see. And what we're going to do is we're going to throw a smoothing capacitor or a rectifying capacitor at the end of that circuit, and we're going to take a look at the inputs, the outputs, how that capacitor affects it. And really where people have a hard time here is tracing those diodes. So if you don't have a background in electronics, maybe it's been a while since you took it in college, or for some people, it might not have been part of their curriculum. This will be a great example right off the bat of talking about just exactly how these diodes work and why they're switching on and off when they are. After that, we're going to talk about three-phase auto transformers. So auto transformers also tends to be kind of a tricky area where you either tend to get it or you don't, and you have a hard time. So we're going to look at three-phase auto transformers. Specifically in this example, it's used on a three-phase transmission line. And we're actually going to go one step further, and we're going to draw that three-phase auto transformer out onto the individual level, where we've got 3 individual single auto transformers. I find that when we draw stuff like that out, it really makes things click and it makes a lot more sense. So really looking forward to this one. Then the 5th one we'll get to is transmission lines, transformers, and line current. So how we're using our A ratio and why we don't need to use a square root of 3 in certain cases, even though it's 3-phase. So I've still been seeing a lot of people getting caught off guard with this. And these are actually those really simple problems where if you're familiar with it, if you practice it, it's really quick to get the right answer and move on. So we're going to touch on that one briefly. Next, 3-phase source and 3-phase load versus a single-phase load. I was a little hesitant to talk about this one tonight because we touched on it briefly on a previous live class, and there's also a case study published on the Power Fundamentals Bootcamp. But bunch of emails since the last class asking to go over this a little bit more in detail today. And I had a couple of people send me example questions, and same thing, they're just asking, hey, it's a single phase load. Do I use line voltage? Do I use phase voltage? How do we know? So we're going to revisit that one more time. We'll draw them both out. We'll start with a 3-phase load. We'll solve like we always do. And then we're going to erase part of our 3-phase load to turn it into a single phase load. And we're going to see how that affects our current, our power, and all that good stuff. Last, if we get time, this is another one we did touch on also in the past. So again, I was a little hesitant to touch on it again because I don't necessarily want to repeat myself, and especially for other people that are good with it. But surprisingly, it's still come up quite a bit in numerous emails. So essentially, this is a 3-phase fault current analysis when we're only given line impedance and line voltage only. Do we use a square root of 3? Do we not use a square root of 3? Stuff like that. Okay, Any questions on tonight's agenda before we jump in and talk about what to focus on this close to the exam? Any questions at all? All right, sounds good. Let's jump into it. So, what should we be focusing on this close to the exam? What I did is I copied and pasted a couple of images and a few of the major talking points from our first class when we talked about the unsuccessful student mindset and the successful student mindset. But right off the top, go ahead and let's talk about what we shouldn't be doing first. Go ahead and enter right in the chat. What are some examples of things that you maybe shouldn't be doing this close to the exam? It can be, especially if you've taken the PE exam before and in hindsight realize, you know what, maybe I was putting a little too much time than I should have. Great answer so far. Craig said sleeping. Kahina said giving up. Carlos said cramming. Zach Shepard being negative. Kate saying trying to learn a new topic. Alex said don't panic. Yes. Great examples. Exactly what I was hoping for. But Craig, I'll counter with you and I'll say, well, I hope you're getting at least a good night's sleep, right? That way we can remember what we learned. But yeah, I definitely don't want to be sleeping when we should be studying. Yeah, these are all great answers. Gary said being overconfident. That's a great one too. Bo said thinking you've studied enough and quit. Yes, absolutely. Would hate to have a overinflated sense of confidence, right? Especially this close. So in my mind, some of the things we shouldn't be doing is the closer you get to the exam, you don't want to get attached on any one topic, right? We don't have months and months ahead of us. So unfortunately, we don't have the luxury of having, tremendous amounts of time to really sit down and read nonstop through theory and really try to understand, the textbook paragraphs so much. The biggest thing I can say is remember that the PE exam, it's a marathon. It's not a sprint. And it's okay to not do good on a topic. In fact, it's okay to do quite poorly on one topic as long as the other topics we do quite well on. And as it turns out, most of the areas I find that people get attached to and they kind of latch on and they spend a disproportionate amount of time on it, it tends to be those really specific and nuanced areas that don't really make up a large portion of the exam. So the bottom line is it's okay if there's a couple of areas that don't feel too good, that just you maybe feel a little uneasy with. That's 100% okay. And to be honest, frankly, if you didn't feel uneasy about at least on one or two of those individual categories, then I would be a little concerned. Then I'd be thinking like, Bo, maybe you have too much confidence. So that's definitely okay. And when I say on one of the topics, I don't mean one of the 10 major topics, but when we break them down into the subcategories, the total of 45 different subcategories, if there's one or two that you're struggling with, it's perfectly okay. Definitely want to make sure that you're feeling comfortable in areas that you can expect to see the most problems. So that's one of my biggest things. Let me see, reading in the chat, Kate said, what if we're still struggling to find certain tables and info in the NEC book? Okay. So the NEC, I would definitely say be careful with, because the NEC, we tend to see two different types of NEC problems. One is going to be a pretty surprising, out of left field code question that you're most likely not familiar with, that it's going to require you to dig and reference. Now, the other type of NEC problems that we're going to see are the ones that we can study for, and it's going to be where we're using the NEC to get a value to solve a different type of problem. For example, given the motor horsepower, the type of motor and the voltage, and looking up the locked rotor amps, so maybe we can size the overcurrent protection. Or maybe we're doing a voltage drop problem and they're going to give us the impedance based off the characteristics of the conductor. And then we have to flip back to, of course, Chapter 9, Table 9 to look up the actual conductor impedance. So those I strongly encourage you to be familiar with, because you're going to see those many different ways. So definitely take the time to find those tables, tab them, do the sample exercises, and make sure you're comfortable with them. All right, what else? Another good thing is, and another good suggestion for the NEC is, if you can, make copies of the index, right? Scan it directly from your book if you can, if you got the time, print it out and put that in your binder. That way, if you are flipping back and forth, you can flip back and forth from that index you printed out, and you can keep your NEC open on the table. It tends to make it kind of easier. All right, those are some great don'ts. What are some good do's? What should we be doing? So we're about 2 weeks away, right? 2 weeks away. What are some things that we should take the time to do now so that we're not stressed and overwhelmed, say the night before the exam or 2 days before the exam? What are some things we should be doing while we still have at least a little bit of breathing room? Go ahead, let me know directly in the chat. Let me know what are the things maybe you've been taking time to do. Sarab said, take time off work. Sure. A lot of people find that towards the end, they take a couple days off so they can spend more time undistracted. I definitely agree with that. Alex said, get organized. Exactly, Alex. That was precisely the answer I was looking for. So what do we mean by get organized? Remember, to do well on this exam, you're going to rely on a tremendous amount of reference material that you've hopefully been able to collect up to this point. You want to make sure all that stuff's organized, right? You don't want to get to the exam, put it all out in front of you and go, oh gosh, I have no idea what's in these different books. So if you haven't taken the time to get at least a little bit comfortable with your reference books, maybe on the surface level, now is definitely a good time to do so. I recommend opening the book, literally reading the table of context. Don't skip the table of contents because up till now, by now you should have a good understanding of just about what's in every category on the test. And so you're going to see those categories or similar versions of it in the table of contents. And that's your best way to know, okay, at least I know maybe I haven't spent, tons of time in this one book, but I know if I'm maybe getting a little desperate, it's the last 15 minutes of the exam, I'm trying to solve those last hard questions that I need to reference for, I'll know I can go to this book for motors. I know I can go to this book for phasor diagrams. I can go to this book for protection, that kind of thing. So you definitely want to make sure all of your references are organized. If you haven't already, figure out how you're going to bring all those references with you. It's not really so simple. A lot of people end up having, a dozen or more books. So I've seen people with luggage on wheels, even all sorts of funny things. I've seen mobile bookshelves. I've seen even people sticking it all in coolers. You can go and I think it's either Staples or Office Max. They have this really nice foldable kind of luggage tote. I've seen a lot of people use that. It's like $10. It's really convenient. That's a great one to use. But make sure you're going to start setting everything aside. If you're planning on staying at a hotel, make sure you already have the reservation. You want to get all the last minute stuff that would stress you out. You want to start taking care of that now before it's going to be a headache. What else? Just reading in the chat, some people said a little bit of exercise and fresh air. Sure. Organizing all of your binders. Absolutely, Rel. Bo said organizing resources so you know where to find them. Yes. If you have been putting together a study binder, like I hope you have, that is a unique reference for you that maybe you've indexed or you've kept a collection of the tougher problems, stuff like that. You want to make sure that's divvied up in a way that if you get a question, you know exactly what tab to flip through. Let's see. Jonathan Zisco, stay hydrated. Your brain works better with water. Yep. So Arb said tabbing, especially in the weaker areas. Sure. If tabs work for you, 100%. Don't go overboard, right? You can kind of blind yourself and have too many tabs, and then that's almost like having no tabs. But yes, if you find yourself going to a certain figure over and over and over, tab it, right? Tab it right in that book. Know where to find it. What else? Jonathan said, verify and print out your seating reservation. Aha, good point. He said, can't get in the door without it. All of it will be worthless if you can't get to your chair. Yes, great point. Print it out, maybe even put it in a Ziploc bag. I don't know, but definitely have that stuff ready to go. Katie said, don't have any loose papers with your reference material. Absolutely. Make sure the day before the exam, at least, make sure you don't have any loose paper. For those of you who are taking it for the first time, the proctors vary in how strict they are, but guaranteed they're going to go through all of your material, and it's going to take them a while before you start. They're going to go through every row and look for any kind of loose paper. And depending on how strict they are, they might try to throw you out of that room. So make sure you have no loose paper. Do not bring any Post-it notes. We already talked about Fitbits, stuff like that. So be careful with what you bring. Get ready, the food you're planning on bringing, all that good stuff. What else? Someone said wheels is probably a good idea if you don't know where the parking lot is. A friend had a bad experience last year carrying a large box for close to a mile walk. Ouch. Yes, very good suggestion, Uri. All right. Besides getting organized, right, we still have a decent amount of time to study, especially if we're taking time off work to do so. So under the do category of what we should be doing, what should we be studying? Should we be studying the hard areas? Should we be going over the areas we're good at? Should we be doing sample exams? Should we be reading? Should we be just solving problem after problem? What kind of things should we be studying up until this point? Yes, exactly. Timed practice exams. Absolutely. If you have not done a practice exam yet, I strongly encourage you to do it as soon as possible, right? You want to give yourself essentially exam conditions. You want to time it. You want to have no interruptions, no distractions. You want to do at least do a morning session one day and an afternoon session in the next day if you can't do it all in one day. But even better, because if you can do it all in one day, you're going to have a better idea of what to expect as far as, okay, what does a 6-minute problem really mean? What kind of pace do I need to work at so that I have enough time? And in all reality, we want to work a little faster than 6 minutes per problem because we want to have some time left over to check our work and to go after those more tricky problems. So doing a timed sample exam, it's going to give you a much better idea of your pace that you have to work. And, you're going to get a little exhausted. It's a long exam. So hitting that wall, getting exhausted now in the beginning, it'll help you at least build a little bit of stamina. It won't be as surprising or unexpected on the actual exam day. All right. Bo said, know that NCEES practice exam like the back of your hand. Yes, I would take that one first if you haven't. That's straight from the horse's mouth. It's your best way to anticipate the verbiage, the ways they might try to trick you, the easy problems with red herrings, just like that. Katie said, I've only been able to do 2-hour blocks, but it's helped out a lot. Great, Katie. Yeah, if you can't do a full-length time practice exam, definitely do what you can. Kahina said, go over notes and read you challenging problems. Yeah, I agree completely with Kahina here. And another thing I'll add to it is don't discount problems that you've already solved and areas that you're comfortable with. You can actually, surprisingly, you can get a lot out of revisiting that and just walking yourself through it. Not necessarily putting your pencil on your paper, especially if you've done it a couple of times, but walking it through in your mind and going through the solution, you'll be surprised. You'll find a lot of problems where you've done in the past. You're going to have that, oh no moment where it's like, how did I do that again? So you want to get that moment out of the way and just kind of refresh on that stuff. So definitely don't knock going over some of your past work. You can go through your past work very, very, very quickly. So it's a tremendous value. Catherine said, after we have done the exams, how should we proceed with the problems we got wrong? Catherine, I would look at if there's any patterns in the ones you got wrong. Were they kind of 3-phase versus single-phase problems? Were they problems where you had to use the square root 3 and maybe you didn't use it correctly? Was it complex numbers, right? Going from, say, polar to rectangular and back and forth. You want to look for those patterns. And I would suggest attacking those patterns first because they're going to have a larger volume and you're likely to get more out of it that way. Practice exams are great because it's a way to really know how far along you're at. And it's a very humbling experience, right? You're going to know, okay, this is clearly my strong area. This is clearly my weak area. The questions you get wrong, you want to spend time with the solution provided by that author and try to see if you can understand the problem with their solution. I find that learning by doing problems and looking at and learning from the solutions on problems I got wrong, for me, I find that to be the most effective. And I also find that to be true for the majority of people. Some people, they don't like that. They'd rather go through longer books. But I really find that doing as many problems as possible and then spending time understanding the ones you got wrong, it's a really quick way to learn. I would also suggest on the sample exams, if you're not sure and you're guessing it, maybe put a star, maybe circle it, put a little arrow, put something next to the number that lets you know, okay, even if I got this one wrong, even if I got this one right, maybe I should treat it like one I got wrong because I kind of just half guessed on it. So maybe if the wording was a little different, I might have gotten it wrong in another variation. So it'll be another good one to study. So that's another good one is don't forget that it's worth it revisiting the questions that you guessed on too. And reading the solutions will either back up what you were thinking or you're going to realize, oh, wow, I really didn't deserve to get this one right. I'm glad I looked at the solution. I won't have to guess on a similar question in the future. All right, what else? What else are some good do's and don'ts? Catherine said, any suggestions on questions that are not problems? Qualitative. Yes, qualitative. If you can set up a relationship with formulas. If they're asking, if you change this variable, what happens to this? Or if current increases, then what happens to this value in this phase? If it's some kind of relationship that you can use formulas to come up with, you can either tell, okay, this is linear, this is going to double, this is going to increase by the exponent. That's one of your surefire ways. And in fact, there's a really good article, Catherine, if you go to the main website, electricalpereview.com, and free articles, there's an article titled Thoughts on the 2016 October exam and Qualitative Questions. And it talks about that quite a bit. The other types of qualitative questions, definition problems, be really careful with, because they're going to say, they love to use the keyword of most nearly, right? Select most nearly from the answers below. What would be the most appropriate use of this, or what is this given scenario? And what you'll find is, out of the 4 answer choices, they're all going to be very similar. And the incorrect answers, they might not be 100% incorrect. It might be slightly incorrect. You really have to know those black and white definitions. So take your time with those. If you're not sure, what do? Skip it, right? Get to the end of the exam, answer the problems that you can get right, get those easy points out of the way, and then go back. Eliminate answers that you know are totally wrong, and then go from there. Katie said, oh, I hate those. Yeah, those tend to be the ones that are going to surprise you. We want to maximize our score essentially on the math problems, because by now I'm hoping your math should be pretty strong, right? You don't have to be a mathematician or anything silly like that, but after doing all these practice problems, you should feel really comfortable with the math. And even questions where you might not know a whole lot about it, you'll find that sometimes you can still come up with the same answer by, manipulating formulas and plugging in different variables. The ones that surprise us are the ones where they ask us a theory question. It's like, oh, wow, I don't even remember seeing that in any of my books. I'm really not sure what I'm going to do here. And another thing is, expect to be surprised. The PE exam, it's such a challenging exam that even when you study from even when you have the time to study from every single different resource, they're going to throw curveballs at you. It's what they're known to do. So don't let it catch you off guard. Expect to be surprised, okay? Because if you're not expecting to be surprised, it's going to take the wind out of your sails a little bit. It's perfectly okay. Even if you only answer 50% of the questions on your first pass, that's perfectly okay. In fact, that's a winning strategy. So don't get discouraged. Don't let your energy levels get down. Whatever you do, don't start to doubt yourself. Expect to see those questions that, frankly, you're just going to go, oh man, I don't even know. It's perfectly okay. What do? We skip it. We move on. Chances are a few of those, we're going to see later questions that give us some light bulb moments and how to answer those, surprisingly. And then, what we're going to do? It's going to be a fight at the very end. The very end, we're going to fight to get every one of those answers right that we can, because we know that passing, the only difference between passing and not passing, it's a difference of one right answer. So that's all. Don't let yourself get surprised, right? What else? All right, looking at the chat. Keen asks, what's the average passing grade? Is it 70%? I don't think they released that. Yep, Jonathan said NCEES does not post passing scores. However, I do know for a fact that 48 out of 80 is not passing, so it's greater than 60. Yeah, it's probably around the 60 or 70%. Mary said October 16th was 66% as posted on their website. Mary, I want to say that's the number of people that passed. I don't think that was the actual passing score. It was the number of people that attempted the exam and left with the passing score. So yeah, and I think the reason why they don't post it, I'm pretty sure it fluctuates. They've got a couple of really tough problems on there. And maybe if it's a problem that a certain majority of people don't get, maybe they eliminate that from the score. It's really hard to tell, right? It's hard to get inside their head. All right, what else? These are all really good things, and I'm glad you guys are. It sounds like you guys are you're well prepared, even if you're somewhat nervous or feeling maybe a little anxious. It sounds like from all the feedback in the chat that you guys are really focusing, so that's good. Let's read over really quickly the unsuccessful student mindset and the successful student mindset. And then we won't waste any more time here. We'll get right to plugging in problems. So who remembers these silly pictures from that first webinar when we talked about the successful and unsuccessful student mindset? I put them here because it's great imagery, right? It kind of sticks in your head a little longer. And the reason why we're going to talk about these mindsets really quick is because we still have, there's still time left to study. For a few of you, if you really think about it this way, for a few of you, there's a good chance that what you do from this point until the PE exam is going to determine whether or not you pass or fail. And I find that holding on to that mindset will really give you the motivation and drive and really ramp up that sense of urgency that really puts your foot on the gas pedal. So think about that. Think about, okay, everything I do from this point up until the PE exam is going to influence whether I pass or fail. So let's see the unsuccessful student mindset. The unsuccessful student, he doesn't want to study any more than he has to, right? He studied 3 hours last night and he put in a bunch of hours last weekend. You know what? I'm going to take a break. The PE exam is about 2 weeks away. Screw it. I've studied enough, right? This is not what we want to do. Instead, we want to over prepare on purpose. We would much rather over prepare now, pass the exam, and never have to go through this again, compared to not study enough, fail, and then go through this process for another exam cycle. So the unsuccessful student risks failing, right? We don't want to risk failing at the outcome of not having to overstudy. The successful student mindset is going to risk putting in extra effort now up front so that they get the results that they want. Who cares about an extra, 10, 20, 30, 40 hours, whatever it may be? Who cares about that now? When you get that piece of paper in the mail that says you passed, all of that's going to disappear, and that's all you're going to care about. And you're going to have a big smile on your face. Next, unsuccessful student does not necessarily believe that passing or failing is up to them, right? Wrong. That's not a mindset we want to hold on to. Successful students fundamentally understand that passing or failing is entirely up to them, right? They're entirely responsible for their outcome. More fuel to the fire of everything that you do between now until the exam may make or break a passing score, so keep that in mind. Next, unsuccessful student takes what they can get attitude, right? We're going to leave that for the unsuccessful students. Instead, we're going to go after what we want with an all or nothing mentality, right? We're not going to leave anything up to chance. Last, the unsuccessful student makes up a large portion of the students that fail and retake. That's true. So again, we want to leave that mindset with the unsuccessful students because we want to be part of the larger portion of students that pass. All right, before moving on, I'm just going to look at the chat here. Jonathan said there's a short YouTube video on the over-engineered, pun intended, process of how they score it. Consult Google for it. I'm going to have to check that out. I guess when you have a group of engineers, it's going to be quite over-engineered. Mary said, okay, I have something in the back of my mind. I have seen that the NCEES sample exam has been the same since 2011. So how do they change their sample exams for the next round? Yeah, Mary, so the best advice I can give you, I think mine's even older because mine, it's the most recent one. It says according to, I think, the 2008 NEC. But you don't really expect to get an exact match from the sample exam to the PE exam. If you're thinking you're going to walk into the PE exam and you're going to have even a handful of questions that are the same from the sample exam that you've been practicing, you're going to be sorely disappointed. The best takeaway from the sample exam is it gives you a very clear-cut idea of how much time you should put into each problem, the exact vocabulary and keywords that they use to describe problems, since that tends to vary a little bit between different authors. It gives you a very clear idea of the variety of problems, the amount per topic. At best, you might have a couple of questions that are similar, but asking for different things, right? A transformer is a transformer. A short circuit problem is a short circuit problem, of course, but don't expect any direct matches. If you are, you're not going to be happy coming to exam day, so be careful. Let's see. All right, let's move on. 2-watt meter method. Who has done a 2-watt meter method problem yet? One of the biggest things I get asked about is where the heck does this come from? This theta minus 30 and this theta plus 30. So these equations right here, we're going to work it out by hand really quickly, and then we're just going to pick a couple of values at random, and we're going to solve. So who can tell me in the chat, 2-watt meter method, is it for a balanced system or an unbalanced system? Trick question. Who can tell me? Go ahead, let me know directly in the chat. Is a 2-watt meter method for balanced or unbalanced? Catherine, I agree with you. Wait, I'm sorry, I spoke too soon. Katie, I agree with you. It can be either. So it doesn't matter, right? That's the beauty of the 2-watt meter method. How about this? How do you know how many watt meters you need to find the total power? Anyone have any ideas? How many watt meters do I need to find the total power? So there's a theorem, I want to say it's called, I think it's like Blond's theorem or something like that, but essentially is the number of wires on your circuit, you need one less watt meter. So here we have a 3-phase system with no neutral. So we need 3 minus 1, we need at least 2 watt meters. All right, so the 2-watt meter method, if this is our source here on the left, and this is our load here on the right, does it matter if these are delta or Y? Does that matter? Who can tell me? It's okay if you're not sure either. And the answer is it doesn't matter. So what we're interested in is we're going to place 2 watt meters. I'm going to call this our A phase, B phase, and C phase. I'm going to say we're going to measure across, let's do the voltage from A to C, and then the current on my A line. And then the next one, we're going to measure the voltage. So that's going to be plus and minus our volts. The second watt meter, we're going to measure the voltage across our B to C from plus to minus. And then we're going to measure the current on the B phase or the B line. So really important. Essentially, it doesn't matter. We can arrange this in several different configurations, but the important part is our watt meters have the same phase as your negative voltage reference. Does everyone see that? In this case, it's C phase. That has to be the negative reference. We can't do a plus and a minus up here. We're going to get the wrong answers. So when we're doing the 2-watt meter method, our negative voltage polarity has to be the same phase, and it's the phase that we're not measuring the current on. So we could have completely flipped these around. We could have had A phase be this common negative voltage polarity phase, but typically this is the most common way it's drawn. Now, let's look at our 2-watt meter formula, right? We know the total power is going to be what? It's going to be the sum of our individual power. So what is this right here? That formula, all it is, it's just a hybrid of our power in watts equals our V magnitude times our I magnitude times our power factor, right? Cosine of that angle, power factor. So why are we subtracting 30 degrees? And why are we adding 30 degrees? Let's look at this. So this first one right here, this would be my watt meter 1, and this would be my watt meter 2. So this is the voltage measured from A to C. Yep, that looks good. This is my current measured on A line. Yep, that looks good. For watt meter 2, it's the voltage magnitude from B to C, here to here. Yep, that looks good. And it's our current on B. That looks good. Does anyone notice anything different about these subscripts? And it's very, very minute. But it's going to be where the shift in angles come from. Does anyone notice anything different about any of these subscripts? And in the meantime, while I wait, I'm going to go ahead and draw a phasor diagram. Katie said they're lowercase. Sure. How about let's draw our voltage. I'm going to draw a phasor diagram. I'm going to assume, let's draw a standard balanced voltage phasor diagram, okay? And it's balanced just to show the relationships. We know that our system that we're measuring power might not necessarily be balanced. First of all, this is definitely a hybrid, right? Because these are line voltage magnitudes and line current magnitudes, and we're not using the square root of 3. So let's look at this. If this was my A to neutral, and this was my B to neutral voltage, and this is my C to neutral voltage, then that would make this my A line, right? Which is really V A to B. And this one would be my V B to C. Is that right? Yep. And then this one right here would be my C line voltage, or really my C to A. Now, regardless if it's a balanced system or not, these relationships are still going to hold true for the individual voltages, right? The phase voltage, the line voltage is still going to have this relationship. So let's look at this. P1 says VAC. Notice how we don't have a VAC, do we? Right? Typically, I'm just going to draw a Y as an example. We go A to B, and then we go B to C, and then we go C to A. So what's important is we're actually measuring what? We're measuring with our positive at A and our negative at C. So we're actually measuring like this. VA to C equals negative C to A, right? Our C to A is our standard polarity, with C is at the positive and A is at the negative. Well, the way we're measuring it, the way we have to configure these watt meters so they satisfy having the same negative voltage polarity on the phase that's not measuring current, we're actually measuring with A as the positive and C as the negative. Does everyone see this difference? Does everyone see that? If you can see that, then 2 watt meters are going to be a breeze for you. But if you've never had this pointed out before, it might take you a while to dig for it. The first time I learned it, it took forever. It was not fun. So let's look at that. How do we go, right? So here's our C line voltage with our polarity from C to A. How do we go from VCA to negative VCA? So if I wanted to draw, I'm going to go ahead, I'm going to pick red for VCA negative. How do I draw VCA negative on my polarity? Heidi said yes. Heidi said multiply it by 1 times 180 degrees. So essentially we can rotate it either counterclockwise or clockwise. It doesn't matter. As long as we rotate it by 180 degrees, either direction is going to get us into the same spot. And before we do that, I'm just going to go ahead and let's draw the line currents so it doesn't get too busy. And for this particular problem, let's say we have a power factor. Let's just say it's lagging for now, okay? So our load, we do know it's lagging. So we know that our currents are going to be behind. I'm only going to draw the A current and the B current because those are the only ones we're interested in for this problem. So if they're lagging, that means that I'm going to say he's right about there. So that's going to be my A line current. And then that's going to put my B line current somewhere right along here. And they're going to have different magnitudes because we are assuming an unbalanced system. Okay, now let's draw our Eric. Heidi said, that's funny, my wife must have been using this computer, and then this is Eric in parentheses. So Heidi's actually Eric. Let's draw this. I'm going to use red. Our negative VAC, right? All we're going to do is we're going to rotate our VAC by negative 180 degrees, or positive. It's going to put us in the same direction of right about there. So this vector right here is VAC. Now, what else? What about our VB to C? Do we have that one? Sure do. Right here, right? Okay, let's look at this power formula. Power factor is what? Power factor is going to equal the cosine of our voltage angle minus our current angle. Usually we use both phase values, but for the watt meter method, since it's a hybrid, right, we're actually measuring across 2 of the phases, we're going to stick with the line values. So let's do watt meter 1 first. So for watt meter 1, our power is going to equal to the magnitude of our line-to-line voltage from VAC, right? That's for watt meter 1 from A to C, times the magnitude of our line current, IA, right? So far, so good. Now, here's IA, here's VAC. How do I find the angle between them, right? Because now the power factor for this expression is going to be the cosine of this angle right here. So let's say if the load is lagging and we know the power factor of the load, then we'll know the theta of that load. So theta of that load would be what? It would be the angle between our current and our phase, remember, our phase voltage. So theta is going to be the angle from here to here. That's theta. And we know we can get from VAN to our rotated VAC by 30 degrees. So this angle is going to be 30 degrees. If you're wondering how we did that, if this was a balanced system, this would be what? This would be negative 120 degrees. If we rotate it in this direction, if we rotate it by a positive 180 degrees, we can say we'll go that way. If we did plus 180 degrees, what would we have? Okay, so what we end up with is a power factor term of cosine times, to get this gap right here, is going to be our theta minus 30 degrees. So that's going to be theta minus 30 degrees. Does everyone see that? Does everyone see where this came from? And that's this formula right here. This is the only tricky part about 2 watt meter method. If you can get this, you are in great shape. Okay, next let's do watt meter 2. That one's going to be a lot easier. We're just going to have our power equals VBC magnitude, no sweat there, times our IB magnitude, again, no sweat there. And now, where are we at? We've got VBC and we've got IB. So how do I find the angle for this term for my second watt meter? Without cheating, without looking at the equation at the top, how do we find that? Does anyone see on the polar diagram where we can find that? So if here's IB, here's VBC, we know that theta is going to be what? Theta is going to be right here, right? Because we've got our line, our B line current, and our B phase voltage. So the distance between them has to be theta. So we want to go theta, and then we want to go an additional 30 degrees. So this one is just theta plus 30 degrees. That's it. That's entirely where these 2 formulas come from. It's that simple. Now, to get the total power of the system, the 3-phase power, all we would do is add our power from watt meter 1, to our power from watt meter 2. And depending on our power factor, right, it's perfectly okay if one of these are negative. Make sure that you add correctly. So if PW2 is negative, we would actually have PW1 minus PW2. So that's perfectly okay if they're negative. And you definitely don't want to accidentally drop that negative symbol, because that's what's going to give you your total correct power. What's another type of question you can expect to get? what if they said, here's a 2-watt meter. Here's the power from a 2-watt meter, right? Total three-phase power was 750 watts. And they might say if VBC is something and IA is something and the power factor of the load is something, find the total power measured by watt meter 2. So what would we do? Well, we could calculate, I'm sorry, these belong on W1. What we would do is we could calculate the value of W1, right, if they gave us these values. And then we would just take that value and we would subtract it from our given value, wouldn't we? And that would give us P W2. So that's pretty common too. That's a really good one to be expected. How does everyone feel with this? We've been at it for getting close to an hour, and if we don't have to do an actual example of this, if everyone's comfortable with it, we've got a lot of other good stuff too. So we can come up with some values and plug them in and solve them, but I feel like you guys are pretty comfortable with this, and I don't want to waste any time because I definitely want to get through all the material. Already said okay with this. Jonathan said, if they equal or don't equal, does that tell you power factor? Jonathan, are you talking about the individual powers? Yep, PW1 versus PW2. It does. There's a table. I don't have it in front of me right now, but essentially, I'm not sure if they'll always equal, but there's sometimes when one might be 0, some's going to be positive, another one's going to be negative. Essentially, what that's telling you is telling you your angle here of this theta. All right, moving on. Look at this one right here. Keen has said if power factor equals 1, does it mean max power? Keen, if power factor equals 1, that means we have a purely resistive load. In other words, if our power factor is 1, then our power in watts equals our power in volt amps, and we have no reactive power. All right, full wave diode bridge rectifiers with a capacitor. So what we're going to do first is we're going to ignore the capacitor first, and we're going to draw our output voltage, and then we're going to take into the effects of that capacitor. First things first, let's look at our input voltage. So let's say this is going to be our peak values. We know that regardless of what's going on over here and in this bridge circuit, regardless, right, our source is going to fluctuate, isn't it? And I'm going to draw it the best I can. Unfortunately, this program doesn't have tools like the other one to draw perfect shapes, but I think we can do a good enough job. So that source, regardless of what's going on in that circuit, is going to fluctuate. And I'm not the best artist freehand. That's a perfect sine wave. So just use your imagination. But it's going to fluctuate from positive to negative, and it's going to reach the values of our peak voltage. Okay. So this is our input voltage. Now, let's look at these diagrams. Let's go with blue. For the time being, we're going to ignore our capacitor and our resistor, and we want to measure our output voltage. So if I had a meter that read positive to negative, what would it look like? So diodes, for those of you that are unfamiliar, a diode, best way to think about it, an ideal diode is going to act like a switch. It's either going to be open or closed. If you have at least, it's about 0.7 volts, I believe. If you have a positive to negative, 0.7 volts across this diode, it's going to act like an open switch. If you have 0 volts, or if they call that reverse biased, then our diode is going to act like an open circuit or an open switch. So as long as you have at least 0.7, right, you could have 1,000 volts. As long as the polarity is from plus to minus, that diode's going to close and it's going to allow the flow of current. It's going to essentially be like a short right here. So let's pretend we're on the positive cycle. So let's pretend on our input voltage, we're from here to here, okay? So that means this point right here in the circuit is going to be positive. But now we have a crossroads, don't we? Tell me in the chat, who's paying attention? Who's good with diodes? Can I go this way? Is my current going to flow in this direction? No, right? Great, of course, good. So what happens? Our path is going to be like this. Let me make it a little bit bigger so it stands out. How's that? Too big? There we go. So here's our path, right? We're on a positive half cycle. We're going to go this way. We're going to go to our load. Next, that current's going to go through our load. It's going to return, right, on the other side of our load, and it's going to get to this point. We have another decision to make. And I find it's easier when we get from this point, it's easier if we work backwards. Let's look at this. Here's our negative voltage, right? Because even though we're working with a positive cycle, we still have a negative reference on the other end of our source. So if we work our way backwards, we know that this point right here is what? Who can tell me in the chat? Is this going to be a positive or negative voltage value, right? If this one's positive, what would this one be? This would be negative, right? Because look, from here to here, it's essentially just measuring what? Across of our source. So if this is negative, who can tell me in the chat, is this going to have to come from the right or from the left, right? If I have a negative right here, which diode is it going to open and which one is it going to close? And you can look here and here, use that as your guide. It's going to be the left one, right? Careful, Carlos, careful. That's going to be, this one's going to short. Because look, we've got negative here. And what do we have here? This is an open circuit, right? Since we have positive is at this point too, right? This diode is going to be open. Since this is positive on this point, this diode is going to be open. So since this point is negative from our source, right? We're still in this position, right? We have a negative on this point. That diode is going to short. All right, so what that means is I'm going to draw my output voltage. And I'm going to draw it blue. But I'm only going to draw it for the positive peaks. Because what happens, right? We're going to have a positive here. And we're going to have another positive here. And we're not done yet either, so don't worry. But essentially, when our source is in a positive half cycle, we're going to get a positive half cycle output. Now, let's look at that same circuit, and I'm going to pick another color, orange, since we already used red. Now, we're going to use our source when it's in a negative cycle. So that means what? That means that these switch places, don't they? Essentially, this is going to be negative, and this is going to be positive, right? So now we're looking at right here. We're looking at this part of our input voltage. Katie said, I'm feeling lost. Is there a section I should read up on? Because I don't feel like I've seen this yet in my studies. Katie, don't feel bad. It's a little tricky if you've never run into it, but let's work our way through this part and we'll see if it helps. Just so everyone knows, I'm hoping to have this module done by tonight. I've filmed about like 6 videos today. It's crazy. I've got a few more to go, but I'm fairly confident it should be there pretty shortly. So Katie, I'll make an announcement when that is available on the course. It'll help. All right, so now we are on a negative cycle, okay? So let's look at our path. And this time, since positive is usually easier to work with, let's work our way backwards. So we've got a negative half cycle, right? We're on this portion. So our polarity on our source is flipped. That means the bottom side is positive. We're at a crossroad. What diode is going to act as the closed circuit now? Which diode is going to be forward biased? The right. Great job, Daniel. Omar, yep. Kahina, Bernie, absolutely. Benny, excuse me. So great. This one's the acts of the short circuit. We get to right here. right? We still have a positive. Again, we're going to ignore our capacitor and our resistor for now. And then we're going to come all the way back to here. Okay, now we have another decision to make. And again, it's easier. Let's just work backwards. So let's get to this point. Is this point positive or negative during our negative half cycle of our input voltage? Who can tell me? Negative, exactly. Great. So furthermore, which diode is that going to force to act like a closed circuit? Which diode is that going to forward bias? The one on the left or the one on the right? Omar said up left. Daniel said up left. Yep, exactly, guys. Great. That's going to shorten, isn't it? And that's going to complete our path. So one of the really cool things is, take a look at this. Look at the voltage. Look at the polarity of our output voltage, right? On our positive cycles, our output voltage is positive and negative. And on our negative input cycles, our polarity on our load, our output, is still positive to negative. So let's draw, I'm going to use that same orange. I'm going to draw the voltage output that the load sees when we're on that same negative half cycle from our input. Guess what? It's going to be positive again. So essentially, this bridge diode, the rectifier circuit, every time our input goes from positive to negative, this acts like a gate. These diodes are just flip-flopping, right? Like this one is closed and this one is closed and these two are open. And then the opposite is true up here. So does everyone see how that works? Before we talk about these capacitors and this resistor, and essentially we're going to get into ripple voltage, does anyone have any questions? Especially Katie. Katie, do you have any questions on this? Because I feel like if you have questions, others will probably have questions too. Tons. Okay, go ahead. This is exactly what this live class is for. We won't spend a ton of time on it, but we can definitely pinpoint a couple of gaps. So Katie, go ahead. Let me know in the chat. Sora said still a bit confused. Let me know what is not making sense yet. Katie said, I'm going to look into the reference article someone point out. Sure. So the biggest thing to remember is look at your symbol, your diode symbol. You want a positive here and a negative here for it to close and act like a closed switch to conduct current. If the opposite is true, if it's reversed biased, right? If our polarity of our voltage across it is switched, that diode's going to open. And we would expect from how these are wired that the opposite diodes are going to be open and closed during both the positive and the negative cycles. All right. Catherine said, how do you get the graph? Catherine, are you asking about the input or the output? Because the input voltage, this is a sinusoidal waveform. This is essentially an AC voltage, is the best way to think of it, right? And the only difference is we're not working in RMS. Don't let that confuse you for the time being if you haven't touched up on that. But essentially all this is, this input right here, this is an AC input. So regardless, right, if we had plus V minus, something that looked like this as an input on a circuit, it would do exactly this. It would oscillate in a sine wave from positive to 0 to negative to 0, right? So our x-axis here is actually our time, right? And the time it takes to complete one cycle would be one complete period, dependent on our frequency. What else? Any other questions on this before we talk about C and R? Kina, I'm not going to talk probably about average voltage here because I want to get through everything, but the videos that are being uploaded will cover that. Catherine said, so with diodes, will it always make everything positive? Well, it depends on how we have it hooked up, right? So if I had a simple circuit like this, I'm going to put a diode in facing backwards, Catherine. And here's my input. So anytime my input is positive, is this diode going to be open or closed? Because essentially I have a positive voltage here and a 0 voltage here since it's open. So Catherine, since you asked, when my input voltage is positive, the way this diode is laid out, would this diode be open or would this diode be closed? Open, great. Okay, now what happens when my voltage is negative? What happens when it's like this? Is this diode going to be open or closed? Closed, exactly. So guess what? The output voltage for this one would be anytime we're positive, we have nothing. And then anytime we're negative, we have our output voltage. So the output for this circuit would look like that. This would be considered a negative half-wave rectifier. Half-wave because, look at this. Essentially, this is our input voltage. Those dashed lines are when that diode is open. Half-wave because out of the positive and negative wave, we're only including one of them in our circuit. Now, if we switch that diode around in that same circuit, then we would have our positive cycles, half cycles, and we wouldn't have our negative half cycles. All right, let's talk about this capacitor and resistor. I hope that helped. I don't want to spend too much of time on it. Catherine said, okay, thanks, it makes more clear, good. Yeah, diodes, they're just a little foreign at first, that's all. Once you get the hang of them, they're no sweat. So let's look at this capacitor. So we're going to use our same output graph. Now, capacitors, essentially, they can act like a voltage source, right? If you put a voltage on a capacitor, that capacitor is going to draw a current until the capacitor is fully charged. If we were to open and give that capacitor a load, that capacitor would then discharge the voltage it was charged to. And as long as it's rated properly, it's going to hold the charge equal to our input voltage. So let's look at the tops of every peak. Let's look at here, here, and here. So at this point right here, our output voltage, right, essentially our voltage across our capacitor and our resistor, is going to equal to our input voltage, right, the peak. However, the second that output voltage dips below the maximum value, our capacitor voltage will be greater than our peak voltage. When that happens, our capacitor is actually going to cause both of these diodes to open, because depending on where we're at in the cycle, if we're here, the voltage here will be greater than the voltage here. So it would act like this, and it would open that diode. Now the capacitor is going to start discharging, right? Because it's no longer hooked up to a source. So it's going to discharge in a linear straight line, just about like that. When it hits this point right here, guess what? At this point right here, VC is equal to wherever we're at in the voltage peak, because this line, which is our VC, our capacitor voltage, is equal to that output voltage we drew. So now as our output voltage grows, that's going to be greater than our capacitor voltage, or you can say our capacitor voltage is going to be smaller, and our capacitor is going to pull a current again, and it's going to start charging. So that capacitor voltage is going to follow our output voltage. Next, we get to this peak right here, and this is the maximum value that output voltage can be without the capacitor, which means the second it starts to go downward, our capacitor, once again, is going to be bigger in voltage, and that's going to cause this diode to open, or if it was on a positive peak, right, this diode would open, right? If VC was bigger than our V peak, it would cause a difference like that and open it. It would cause it to reverse bias. So then what's going to happen? Well, now our capacitor is no longer hooked up to a source, so all it can do is just going to start discharging the voltage that it stored up, and it's going to discharge it to the load. So the load is going to draw a current from that capacitor. The capacitor essentially acts as the source up until the point where our output voltage meets up exactly and equaling our capacitor voltage, right? And at that point, we're going to start to charge that capacitor again. And this pattern will go on and on and on and on. So in this circuit would be a DC rectifier, right? That capacitor gives us almost it's going to be, you're going to have ripple there, but our capacitor essentially has a straight line. Now, any questions about this? Because for some people, this can be very challenging. So if you have any questions, now is the time to ask them and we can address it live. The biggest way I understand it is if my capacitor voltage is greater, the diodes in this circuit feeding the capacitor are going to open, right? Essentially turning it into this. Let me scroll down. Essentially, it's going to look like this. Now we have a plus VC minus and an open circuit on this end, and our capacitor acts as a voltage source, and our resistor is going to draw a load. All right. I think you guys will find that when you find these problems and you're setting them up a little bit, if you come back to what we talked about here, it'll become a lot more clear. All right. Any questions on this before we move on? And we won't spend a ton of time getting too detailed in here because right now I just want to touch on the high level. Otherwise, we'll be here forever. And we definitely have a lot of other really good stuff. Jonathan Zisco said equation for ripple. I'll have that posted in the course. That should be posted either by tonight or tomorrow. I just have a few more. I'm going to edit some videos while I upload this video tonight. So I know the PE exam's coming around the corner, and I want to make sure I get that to you guys. All right. For some of us, this should be very familiar. Sarab asks, are thyristors similar in concept? They're a little different, but essentially they're going to open or close. Thyristors, though, they require an external signal to open. I'm sorry, to close. Carlos said, do we see this type of problem for VFDs? Yep. Thyristors, same as an SCR or a silicone controlled rectifier. Those are the switches in a VFD that causes those pulses. Because remember, a VFD wants to do what? A VFD is essentially, it's like an inverter. And a VFD controls the speed by controlling the frequency. Remember that equation with poles and frequency to get speed in our motor chapter? So a VFD is going to be changing the frequency. But since the VFD is not a true AC source, right? If this was a true AC source, a VFD does, it sends pulses. So it sends big on or off pulses, right? It sends individual square waves really quickly. And it can either send bigger ones or smaller ones with a varying wavelength. And essentially, to the machine, it's almost no different than seeing an AC sign. And a really cool thing here to talk about too is you'll see, I think they call it volts per hertz or V per F. This is a really interesting ratio too. A lot of times if you have a VFD, you can set the VFD to control in V ratio F mode. And essentially, let's look at this. When we have an inductor and it creates a magnetic field, say for the case of a motor or a transformer, if that inductor is rated in henries, if we want to get to our ohms, our X of L, then we multiply that henry by what? WH, which is the same as 2 pi times our frequency F times H. Does everyone see that? And our magnetic field ratio grows in relationship with our current. So this inductor, if it's drawing a current, I is going to equal to what? V over X of L. So I in our magnetic field is going to be directly related to V divided by 2 pi F times the actual inductance. And so this is where things get interesting. So if we raise our henries, or if we raise our frequency, our I is going to drop down, right? What happens if we lower our frequency? So let's say we've got a motor that's being fed by a VFD like this. So let's say it's a 480 volt three-phase motor, right? Our supply voltage, that doesn't change. So this is constant. What are we changing when we control a motor with a VFD? Variable what? Variable frequency drive. So we're changing our frequency. So what happens when we slow that motor down? If we slow that motor down in frequency, guess who's going to jump up? Our current, which is going to do what? It's going to grow our magnetic field. So if, what they do for volts per hertz is that VFD will actually vary the output voltage along with the speed, so that your V divided by F is always going to be a set constant that you decide. So this relationship is really good to know. This is a fantastic qualitative question. You could see, okay, what happens if I vary the so how about if voltage is held constant, but the frequency is decreased without matching the voltage, what happens? Can the magnetic field grow beyond reason? Can it derate? That kind of thing. So that's a really good relationship to know. All right, I'm actually going to stick that on another page. That way it's there in the notes before we talk about our auto transformers. So let me copy this, and I'm just going to stick it right here. And let's call that volts per hertz. It's actually a great question. I'm glad you asked it. All right, auto transformers. So auto transformers can be quite a big pain point. Here's a quick sample example. A three-phase auto transformer rated for 135 MVA is used at the end of a long three-phase transmission line to regulate the voltage from 210 kV to 230 kV. I'm still getting a lot of emails about, is this line voltage, is this phase voltage, how do I tell? So someone let me know right now in the chat. Are these my line voltage values or are these my phase voltage values, right? And we can reread the problem again. At the end of a long three-phase transmission line, these are line voltage, right? Exactly. Why? Because it's a three-phase transmission line, and it'd be kind of silly to give you the phase values of a three-phase line, right? Okay, what else? Everyone's familiar with seeing a three-phase transformer. And essentially, it's just three single-phase transformers like this, right? Everyone's familiar with this. And then what happens on this side, how they're connected, and what happens on this side depends if it's delta or Y. And if this side is delta or Y, essentially you've got your three lines coming in and your three lines going out, right? So how do we do the same thing for an auto transformer? Let's look at that. So an auto transformer, right, looks something like this. Where this is my primary voltage, and this is my secondary voltage. Now, trick question. What was the rating of that three-phase line? It said, okay, no sweat, three-phase auto transformer rated for 135, and it regulates the voltage on the three-phase line, keyword three-phase, from 210 kV to 230 kV. So our three-phase auto transformer is going from 210 kV, stepping it up to 230 kV. So if this is our primary and this is our secondary, who can tell me in the chat, what's my voltage on across my primary terminals of this auto transformer? And we're going to say this is a single phase out of three. Who can tell me? If you don't know, feel free to know. I got no problem with that. Who can tell me? Yikes, 440. Who can tell me what's my primary voltage? 230. Remember, these actually might be flipped around. Let's do this. You caught me. Let's say we're regulating it down from 330 kV to 210. Sorry. Just for the sake of this problem, because I drew it backwards, I'm used to drawing it like this. How do we know that this side is going to have higher voltage? Because there's more windings, right? Your winding ratio corresponds to your voltage ratio, since you've got the sum of both windings on a primary side and just a common winding on the secondary side. The secondary side would have to be smaller. There we go. Craig said 230 divided by the square root of 3. Bingo. Great job, Craig. That was exactly the answer I'm looking for. So if we're using a three-phase auto transformer to regulate the line of a three-phase transmission line, why would we use the square root of 3? Why is our primary voltage actually our phase voltage? Any idea? Rahul said no. Exactly. Craig said because there's 3 transformers. So I think there's even a sample exam where it gives the 3-phase bus ratings or transmission line ratings on both sides, but it gives you the line voltages. So it's a bit misleading, right? Because they leave it up to you to actually realize, hey, even though they're giving me the 3-phase line voltage of the transmission line or the bus, and they're showing it directly underneath a single-phase auto transformer, which is kind of tricky, I know that the voltage across my auto transformer is actually my phase voltage. So we're going to see where that comes from. So we said this was just 1 phase out of 3, right? Because what's a 3-phase auto transformer? It's really just 3 individual single-phase auto transformers in a single tank, right? Just like those big transformers at, say, utility substation, a 3-phase transformer. That's really just 3 individual single-phase transformers on a common core in the same tank. So let's take this and make 3 of them. Now, I'm going to pick a different color for our 230 kV side. Let's pick green. And let's move this over to the right just a bit. There we go. Can everyone still see that okay? Do I need to zoom out a little bit? I can if I need to. So let's draw our 3 phase lines. Here's A. Here's B. And here is, of course, C. Now, we know in an auto transformer, our primary current is right here, right? That's why I connected my transmission line phases to that side. And we also know the output current is where? Output current's on that side, isn't it? So now let's go with hot pink. Let's draw our lines on the other side. There's A, there's B, and there's C. So I know from A to B on the left-hand side is going to be 210 kV, right? A to B, B to C. That's the magnitude of my line voltage on my transmission line after it's been regulated by the auto transformer. Likewise, on my primary side, I know that my magnitude of my voltage from A to B, my line voltage, is 230 kV. Right? Everyone good with this so far? Now, in order to get this auto transformer to work, what do? These are actually our neutral. Look at that. So even if, say we've got a really long 3-phase transmission line and we don't really care about using, the neutral, right? We don't care about having a phase voltage. Even if that's the case, we still need the neutrals of the auto transformers connected in order to properly either step up or step down our voltage. So even though we're not using the neutral on this side, guess what? It's still connected and still there. So if you were driving down, let's see, is yellow to, ooh, that's not a good color. That'll work. So if you're driving down the road and you saw a 3-phase auto transformer on a 230 to 210 kV line, here's your 3-phase auto transformer. So this is your 3-phase auto transformer. So that phase voltage is never used for that transmission line, is it? That phase voltage, right, from plus to minus, plus B to neutral, C to neutral, or A to neutral, or here A, B, or C to neutral, it's never used outside the auto transformer, but it's still required to be connected. So when we look at the single phase equivalent circuit, or if we look at just one out of the three, let's do a color that stands out. How's that? So when we're looking at a single one out of the three, we have to make sure we use what? We have to make sure we use our phase voltage values. Otherwise, we're going to accidentally put our line values here, and our equations are going to be all messed up. So does everyone see that relationship? Does everyone see how that works? Any questions at all about how we hooked this up and how we determined so what if we didn't know? What if we didn't know, gee, I don't know, is this my line voltage? Is this my phase voltage? Well, let me draw it out. Arturo said good. Carlos said good. Okay. How about this, guys? I've got another trick question for you. So the rating of that auto transformer, and I'm going to go ahead and cross this out since I did draw it as a step down on accident. We'll say 230 kV to 210. So that rating of the auto transformer was what? 135 MVA. Okay. What's the rating of this single phase auto transformer right here? Who can tell me? So if the rating of my exactly, Bo said 45. Good job, Swarb. Exactly. Good. Very good. So if my 3-phase auto transformer is rated for 135 MVA, then when we're looking at just the single phase equivalent circuit, aka if we had to solve for the currents or anything else going on in the circuit, then our single phase rating would be 135 divided by 3, or 45 MVA. And guess what? Now that we know the MVA and we know the voltage, could we calculate the current? Sure we could, right? We know our primary voltage, we know our secondary voltage. That's when we get to use A equals N1 over N2, which equals our primary voltage over our secondary voltage, which equals our secondary current over our primary current. And we also know the formula that says for single phase, our MVA equals our voltage times our current. We know our power in the total auto transformer for the single phase. We know our voltage on both sides. So if I solve for I and I use my primary voltage, guess what? That's going to give us our primary current. And if I solve for I and I plug in my secondary voltage, then that's going to give me my secondary current. And guess what? That secondary current is going to equal to what? That's going to equal to the 3-phase line current. How about that? Does everyone see that? So even though it's the secondary current of the single phase from my auto transformer, that's still going to equal my 3-phase line current. So auto transformers are really tricky. Once you get auto transformers down, Pat, is when you know you've got all of your single phase and three phase relationships sound, because you're essentially going back and forth, and it really requires you to draw things out, look at formulas, and really take an objective look at what's what. All right, any questions before we move on? Any questions at all? The chat is getting a little quiet, and that scares me because I know that a few of you are still scratching your head. If you're scratching your head, please, now is the time to ask me. It's much more effective when you got me, right? You got me. Can't go anywhere. It's much more effective to ask me now. Okay, everyone says they're good. I'm assuming you are all masters on auto transformers. And really quick, don't forget, you can do the same for your delta or Y connections for a three-phase transformer. All right, moving on. Transmission lines, transformers, and line current using our A ratio and the square root of 3. So this is still catching a few of you. So I want to make sure we talk about it. This is actually really simple. Okay, let's say we've got a generator that's feeding a load that's drawing 110 amps. And in between that load and our generator is 3 transformers. For the sake of simplicity, we are going to neglect or ignore any other load. So for the sake of simplicity, in an ideal world, which of course doesn't exist, we're only concerned with this generator and our 3 transformers. Now, just like we did before, we can draw these out. But more importantly, how do I find this current right here? Who can tell me? How do I find my I in red? Marcus said I secondary equals I three phase. Oh, Marcus on the auto transformer. For that particular example, yes. Keena said 12 divided by, it looks like 11. Oh, 12. I2 over I1 equals A. Yep. Great, Keena. Sorry, I couldn't read that. Alex said A. Absolutely. Bo said you have to divide by 1.732, aka square root of 3 first. Gotcha, Bo. This is exactly why I wanted to do this. Bo, why do you need to divide by the square root of 3? Be very careful. Arturo said reference the 110 to the primary side. Correct, Arturo. Bo said turns ratio is based on phase voltage and current. True. How about this, though? All right. I'm going to copy from up top so it's quicker. Let's look at this, Bo. Be very careful with that. Right. It doesn't matter, but we want to make sure we can figure out why, right? We don't want to just blindly accept it. If we can prove it on paper, we're going to remember it and it's going to get us out of a jam. So let's say this is T3 and T3 is a delta to delta, okay? So let's look at, sometimes I don't draw these right, so let me know. Here's our, call that A. We'll say that this is going to be B, and here's C. We'll connect them all together. Does this look good to everyone else? Look good so far to everybody? So then here's our A. Here's, hang on, you guys let me draw that funny. I didn't even notice I did that. How did I get C there? Doesn't matter, but A, B, and C. All right, here's our B. Here's our C. And last, we'll connect them all together to finish that delta. So who can tell me my 110 amps on that diagram up top? Where is that 110 on this diagram down here? I'm going to finish this up while I wait. Okay, this 110 right here, where's that on this diagram right here? Essentially, what did we just draw? We just drew this, right? So where's this 110 amps? That 110 is going to be right here, isn't it? this phase, on this phase, and on our C phase, right? When we see a single line diagram representing a three-phase system, and we say a line current of such, we're assuming it's balanced. So in other words, that 110 amps is going to be on each line. Great. Now, we're looking for this current, aren't we? So essentially, this current is entering here and here and here, right? Careful, because this would be the phase current, but we're not concerned about that. And here we have, this is a 220 kV to 480 kV. Another way to look at this is if we drew it like this. Right? Couldn't this also be another way we could draw this relationship? Now, on this way, when we look at it, where's my 110? My 110 is right here still, right? It hasn't changed. And that exists on all three phases. So who can tell me really quickly, if I asked you what was the magnitude on any of the phase currents with inside this delta winding, how would I find that? If I asked you what was the magnitude of the phase current, if we know the magnitude of the line current, right, we divide by the square root of 3, great. But what if we don't care about those phase currents, right? What if we just want to know this current right here? Then we don't need the square root of 3, right? Because our line current on this side is going to be proportional to our line current on this side. So all we do is we know this is a step down transformer. And so if our voltage is going down on this side, then on this side, is our current going to be bigger or smaller? Our current is going to be less, right? If our voltage is bigger, right? P equals to, let's say S equals to VI, and S1 equals S2. So if our voltage is higher on this side and lower on this side, then our current is going to be the opposite, right? So if we want to find this I right here, here's our 110 amps. And now, in order to make I smaller, what would the ratio of this voltage have to be? 480 would have to be on top, wouldn't it? And 220 would have to be on the bottom. Does everyone agree? Does everyone see that? So now go ahead, someone, you've probably already found it already. Go ahead, let me know in the chat what you found for that line current. And in the meantime, I'm entering it on my calculator and we're gonna check our work together. Don't forget your units. You've got kV on the left and you've got 480 volts on the right. So go ahead and let me know. Yep, Omar, you are correct. That's the same answer I got, 0.24 amps. Great. All right, any questions here? Does anyone have any questions? This is one of those areas where the math is simple, but that tricky square root of 3 comes up and we get so comfortable with using it for three-phase that we want to make sure we don't use it on accident. So Rob said, how about if the question asks for the current at the generator? Sure. So Rob, all you would do, now we found this I, right? We would take it back one more time. We would find this I. We would take it back one more time. We would find this I. Now, I'm kind of glad you asked that question because that's exactly what we're leading up to. Now, and I'm going to add a new page. What would happen if, remember our I'm going to draw a single phase equivalent circuit for our generator. And trick question, if this is my single phase equivalent circuit of that generator up top, right? And let's just say the rating there was what, 13.8 kV on the primary side of that transformer. So if that was 13.8 stepped up to 69 kV. Sorry if I'm moving too quickly. All right, trick question. What's E? You don't have to do the math. You can just type out what you need to get E if you know it. Someone tell me what's E in the chat. If this is our single phase equivalent circuit for our generator, yes, Kahina and Michael, great job. Square root of 3, right? We know this has to be phase voltage. Since it's a single phase equivalent circuit, we're essentially looking at it with respect to the neutral. So guess what? Now, if that question asks, what is the internal generator current? So what is the internal current? What is the stator current? What is the per phase current? What is the line current? I go on and on. Current of the generator. If the question asks for that, how would we find that? So we took our I from here at our load to this transmission line, to this transmission line. Okay, now we're at the generator side. So let's scroll back down. So we found this I right here, right? Through all those transformers, through all those A ratios. So where on here is my internal current of my generator? Where's my stator current of the generator? My per phase current of the generator? Where's my line current? I'll give you a hint, they're all the same thing, right? These are all the same. Wouldn't that be this right here? Does everyone agree? So if you were asked for what's the internal current of that generator, what's the stator current? Since this essentially, we're not even showing the rotor, right? This is the stator side of that equivalent circuit. Or what is the per phase? Or hey, what's the line current? How about what's the terminal? That's a good one. What's the terminal current? It's gonna be that same A value, or I'm sorry, it's gonna be that same I value. Does everyone see that? This I is the same. Craig said, confuse myself. Would the current transformation be the same for all transformers, even delta to Y? It should be. I caught myself when I drew this. I got to look at some references. I think there is a specific change in. I know there's a slight different change in voltage and current, but I think that more has to do with the phase angle. But I caught myself when I was drawing that, and I kind of questioned myself for a second. I'm going to take a look at that after this. And if any of this is different because of the delta delta or delta Y configuration, I'll let you know. I'll send an addendum like last time. I think that should just be for the phase angle, but I could be wrong. But yeah, if there is an issue, I will not leave that unchecked. No problem. Heidi said, Eric asks, since we're talking about equivalent circuits, when do you use an equivalent circuit as opposed to a synchronous or induction motor circuit? Eric, that totally depends on the machine. So this is a synchronous generator equivalent circuit, looking just at the stator. Any large scale generators are always going to be synchronous generator. Induction generators are not economical because they actually require reactive power to create that magnetic field in the winding. They will require it from the terminal that they're connected to versus I think I got that right, versus a synchronous generator. That reactive power, it's coming from the excited rotor. So large scale generators, power plants, gas generators, turbo generators, steam driven generators, they're going to be synchronous unless you're out in the middle of the desert somewhere and you're you're stranded and you are in dire shape and you find a motor and you can MacGyver it to run backwards into an induction generator and you somehow find a way to supply it reactive power, it's always going to be a synchronous motor. Or sorry, synchronous generator. What else? Swarb said, sorry, I missed the part on current at the generator. Did you say that would be the current at the terminal? Yep. We added terminal down here. Essentially, that I that we found all the way from the load is the same as this I right here in that phase. Because remember, this is single phase, right? So we actually have, this is single phase out of 3 again. All right. And how about another trick question? We found this I, whatever it is, don't care for right now, we'll just call it I. What if I asked you to find what was, instead of asking for the phase, internal phase current of the generator, what about the magnitude of the phase current inside the delta winding of this transformer? Who can tell me in the chat? And if you get this right, I'll know it's starting to click for you. Bo, especially, I'm looking at you. Bo, what would the phase magnitude be inside this delta winding? If we knew I, if we know the current along this line right here, who can tell me in the chat? Careful, Craig. Careful, Swab. There we go. Great, Mary. I divided by the square root of 3. Exactly. Why is that? Let's pretend this delta winding right here is this delta winding. Ignore this delta right here. That I per phase is coming into a delta winding, which means it's going to get smaller. It's going to go through the phases. It's going to be translated by a ratio of A to these phases, either step up or step down, and then it's going to grow by the square root of 3, and then it's going to exit that delta. How about this? One more chance. I'm going to try to trick you guys one more time before we move on. This I right here, okay? What about this I? So if we know the current along this line right here, let me pick another color. If we know this I, I'm not going to say it out loud, but all I'm going to ask is tell me, and again, just write it out in the formula. What's my phase current inside that winding of that transformer? This one right here. Good. Same. Exactly. Good job. Yep. Exactly, Mary. Yes. Jonathan Disco said, would we worry about percent impedance if they were listed? To be honest, the only time, well, I'm not going to say the only time, right? But for the most part, when you're dealing with transformers, the percent impedance is going to come into play when you're doing fault current analysis problems, or another good one is when you have like load sharing transformers. So if you have 2 in parallel like this, your percent impedance of each one and the kVA rating of each one, or the MVA rating of each one, those 2 factors will decide the ratio that each contributes to the load current. So that's where you'll need to work with that. But no, in normal conditions, I'll say ideal normal, right? I'll cover my butt. In ideal normal conditions, your percent impedance is going to have no effect on what? It's going to have no effect on your current and your voltage from primary to secondary, right? Because the only thing that has an effect on that is what? Is your ratio. That's all. Sorab asks, when would we want to make sure we are working on a same base? Sorab, anytime you're adding numbers that are already in the per unit system, even though the per unit system is unitless by definition, they have associated bases. So sometimes you're going to need to change a base, right? That's what base changes are for. Just be careful. Aaron said, could you reduce steps between essentially the other transformers? Let's see. Between the 220-69 and the 69-13-8. Yeah. Yes, you could. The math would work out, wouldn't it, Aaron? The 69 on the secondary of T1 and the 69 on the positive of T2, which, look at that, I mislabeled. Those 2 would cancel each other out. So yeah, Aaron, you're absolutely right. As long as you weren't looking for the current in between the 2, you're right. Rel asks, can you go over your trick question one more time? Which one in specifically, Rel? Sarab said, can you cover a question that would require a base change? Sure. How about Sarab, shoot me an email after this. And I don't think we've covered that live, so that'd actually be a great one to do. We'll do that on the next session. I don't have anything prepared with me tonight for that, but that's definitely something we can talk about. And since we haven't, I think that's actually a fantastic one. So please shoot me an email. Remind me. If you got another tab over, feel free to do it now. I just don't want to mess with the screen share and get it all messed up. Rel said the first I magnitude. Gotcha. So Rel, the trick questions were essentially coming from here to here and then asking for, how about this, Rel? Rel, if you know this current right here, I, and you're asked the internal phase current of this winding, how would you find it? And I'll help you out. You have to look at, is this winding here a delta or a Y? And how does a delta or a Y change what happens to the current? Mary said, I haven't checked the numbers, but having the MVA and the voltage for the different transformers, would we calculate I using MVA divided by the square root of 3? Good question, Mary. Let's talk about that. Arturo said current is 240 amps. It's possible. I didn't go that far, Arturo, so I don't know off the top of my head. We could do it. You would just keep using this factor of A. Let's focus in on what Mary talked about, because that's a really good point. Let's draw this. How about this, Mary? Let me know if this is what you're thinking, because if it is, then we're on the same page. So let's say we've got a transformer, right? We'll say 3-phase, 45 MVA. And let's say 13.8 kV, step down to 4160 volts, right? Pretty common. Now, when we calculate I using, I'm going to write it out just like you wrote it in the chat. We'll talk about it. Times the square root 3 times a V. Now, since of this, and I'm going to rewrite this because I'm a stickler for our notation. Let's just say our I magnitude equals our S magnitude divided by square root 3 times our V magnitude. And since this square root 3 is here, we know we're dealing with our line values or our 3-phase values. So I'll stick that there and I'll call this our S 3-phase. Now, let's look at this. This S value right here, this MVA, what exactly is that number? What is that number telling me about this transformer, right? Isn't that the power rating? So notice this equation, you don't have to use a power rating. In this example, if we plug in our transformer numbers, then it would be our power rating. So I want to make that clear. But essentially, what is this 45 MVA? If I plugged in that 45 MVA, that would be my power rating. In fact, I'm going to just take that off because I don't want to confuse anyone. Let's draw that note up here in red. So that 45 MVA, that's my power rating, right? What does that mean? What does it mean to have a power rating of a transformer? Who can tell me? What does it mean to have a power rating? Yes, Aaron, amount capable of supplying. Kahina, maximum power. Absolutely. Great. So who asked that question? Was that Mary? Yep. So Mary, essentially, that's the maximum amount of power, right? That's the maximum amount of current that this transformer is going to step down before exceeding 45 MVA and overheating. So if I plug in my power rating and I use whatever my voltage is, then what do you think that's going to tell me about what's I going to be if we want to get really technical? And then we'll talk about why that's important. So if we use our power rating, so if we use max power rating, yes, rated current, exactly. That makes I our rated current. In other words, that's going to be your full load amps or your maximum current that your transformer is going to either deliver to your load on the secondary side or step down from your primary side only because this is a step down transformer. Now, what about if this transformer, so let's go ahead, let's calculate I full load amps really quick. Someone help me out. Solve it and let me know I got it right. So let's do 45 MVA divided by square root 3 times our secondary line voltage. So 4160 volts. What's my FLA? Craig said, well, that's a lot. Okay. Carlos got the same answer. I'm going to take your guys' word for it. So don't leave me astray. 6,245 amps. Now, huge value, right? What if this transformer was approximately 50% loaded? And let's just say we had an I secondary of, let's say 3,000 amps, okay? What is my primary current going to be? How do we solve our primary current? Ratio, exactly. We use A, don't we? Right? Now, that seems very intuitive. Let me show you when this messes people up. And expect to see at least one question like this because they'll test you. They want to really make sure you know your A ratio. Okay, so this is a 13.8 kV. We're stepping down to 4160, right? Uh-oh. Let's look at this. Catherine said 904 amps, okay? And just checking in my head, I know my voltage is bigger, so I expect my amps to be less. So, Catherine, taking your word for it. Now, here's my generator. Say this is a lousy generator. What if this generator is only outputting 13.5 kV line to line or three phase? What's my voltage here? Now what? Hoping it'll be easy because we just did a very similar answer with our current. A lot of times this is going to mess people up. What would my V secondary be? Any guesses? No? I hope I didn't stump you guys. I hope some of you guys got it. Craig said 4,069. Beautiful. Catherine said 4,069.6. Yep. Omar said 4160. Careful, Omar. Remember, this is just the rating of that transformer. Essentially, it's built to be able to safely handle these voltages in normal operating conditions. And it's built with a turns ratio such that if you apply 13.8 kV, it's going to give you 4160 on the other side. But when we apply 13.5 kV, we're going to get something else. So let's see how we do this. We use our A again. So now I have, if this is a step down transformer, right? What do I need to multiply, right? I know my voltage is going to get smaller. In other words, you can use this all day. N1 over N2 equals V1 over V2 equals I2 over I1. And I only know that because I've had to write it so many times. But if you want to get good at conceptually knowing how to use this stuff, so I'm looking at this, I know my voltage is going to step down. I know A is a ratio of the two, but sometimes one's going to be over the other, and I don't want to make a mistake. So if I'm stepping down, I need to divide by the bigger number, right? So if I'm stepping down, the bigger number is 13.8 kV and 4160 is on top. Does everyone see how I kind of did that in my head intuitively? I find this to be way easier just thinking about, okay, is it going to be bigger or smaller? If that's the case, then the bigger number has to be on top or the bigger number has to be on bottom versus when I do this, it messes me up sometimes. So good. A lot of people are saying yes. Those are the tricks that are going to save you time on the exam And you're going to write out the formula anyways, right? Because that's how you're going to avoid mistakes. But those kind of ways of kind of intuitively understanding the math, that's how you're going to catch yourself. You're going to go, oh man, I need to back up here. I just made a mistake. That's how you're going to get extra points in the exam. All right, so let's plug this in. Let's see what our actual voltage on the secondary if we apply a true applied voltage of 13.5. So someone help me out, do the math with me, and let me know that I solved it correctly. So in my calculator right now, I'm punching in 13.5 times e to the 3 times, in parentheses, 4160 divided by 13.8 e to the 3. What did you guys come up with? I saw a couple of you already answered. Who else? Anyone else doing this with me? Awesome. Yep, 4,069. Omar, is that going to be 0.5 if you're going to round to the nearest tenth of a volt, or should that be 0.6? Careful. Sometimes rounding will make or break a problem. If you've got, that's another good thing we can talk about too. So here's 4,069. I'm going to round to 0.6 volts. So slightly less. Here's another quick way to know that we're in the right ballpark. So if I give it a true 13.8 kV, I get a true 4160 output. However, if I give it slightly less, I'm expecting to get what? I'm expecting to get slightly less on the output. So if we look at it, look at that, right? 4,069.6 is slightly less than 4160. Another quick way to mentally just check your work. There you go. Michael Cook. I'm not even going to try to read all those numbers, but yes, that is definitely the exact voltage. I think you've got about 10 decimal places there. Yes. Jonathan said those 3 nanovolts make it. All right, everyone good here before we move on? It's about 10:30. We're going to try to get to the end here if we can. We might have to pick up the pace a little bit, but I want to make sure we cover this stuff in detail. Does everyone see how these little things can, if you're not careful, even the simple ones can bite you? These are the easy ones, right? These are the questions we want to rely on to get right, to offset any of those really unfair hard ones. So I want to make sure all these, even the easy ones, they're going to try to trick you. All right, 3-phase source, 3-phase load versus single-phase load. So I drew this really quick while we were getting ready. It's not the best, but I think it illustrates the point. Now, this is a 3-phase load. Here's my 3-phase source. We're going to say the whole system's balanced and positive just to make this easy. So let's say our line voltage, someone give me a line voltage. What's a really common line voltage? Someone give me a line, 480, great. Wow, look at that, all you guys picked 480. It's funny, I was thinking the same thing too, it's kind of strange. So we've got plus 480 volts minus. Someone give me a small impedance, nothing too crazy, but just single digits are fine. Give me a, it can be a leading or lagging, don't care. Omar, you got the first one, 3 plus 4J, great. So all of these equal the same 3.J4. Now, some of you are going to get this wrong, and I want you to be participating, because if you get this wrong, I want to make sure we correct it here, because this is going to be a very, very, very fundamental relationship. What does I equal? Let me know directly in the chat. You don't give me the number, right? Don't calculate it. Just give me the relationship. What does I equal? And I encourage, so we got 27 people listening live, and it's kind of funny because it's the same, maybe 8 or 9 of us that are going back and forth. All of you guys sit in the back, I encourage you to join in. I guarantee you the 8 or so that are participating, and it's the same group, I guarantee you these are the folks that are really going to be benefiting from this and are going to be getting those extra points. So if you're sitting back, you're probably smiling listening to you say this. Now's the time to jump in. All right, so Arb said I line equals I phase. Kahina said 480 divided by the square root of 3. Great, Kahina, that's what I was looking for. So Craig and Bernie, you said V over Z. Did you mean 480 volts, or did you mean something else? Tony said V to N over Z. Great, Tony, fantastic. Arturo said I'm too slow. You got Arturo. Mary, great, 480 divided by the square root of 3 times Z. Fantastic. Shamil, fantastic. Bo said, I agree with John. Great. So Craig and Benny Harris, I want to single you guys out for a second. I'm not picking on you, but again, I'm looking for the guys and girls that are going to get this wrong because I want to correct it. I don't want you to get this wrong anymore. Craig and Benny, you both said V over Z. What V, right? Because we technically have 2 different V's we can use. Craig said, I have no idea what you asked. My stamina's gone. Craig, how do you think I feel? These things wear me out by the time we get through. So the answer, of course, is I is going to equal to 480 volts divided by the square root of 3 times 3 plus J4. In other words, we said I is equal to 480 volts divided by the square root of 3 divided by our impedance. So what we just did is we used, here's our neutral. We used our phase voltage, didn't we? Now, that's 101. I hope all you are familiar with this. What happens when we do this? I'm going to make a brand new page. All right. Let's keep. What was Z? Z was 3 plus J4. All right. So Z was, I forgot it again, 3 plus J4. There we go. Now, we've got a single phase load. So I'm going to do this. I'll leave that. Okay. We're going to use the same value for impedance just for fun, but it doesn't really matter. Now let's go ahead. Let's connect this single phase load. Okay. Now let me know in the chat. Someone tell me what our current is. Yes, exactly. 480 over Z. Now, is this a 3-phase source or is this a single phase source? It's still a 3-phase source, right? This is a single phase load. When we're working, if you're not sure, what do? We go back to Ohm's law, don't we? So here's my 3 plus J4. If I want to find this current, I need to know the voltage across, right? Easy. Voltage across, here to here is our line voltage, 480. Saurabh said, this is the same as if the question asks if one phase is open. Careful, because there's open delta is something that exists, and there's also an open Y that I recently found out about, but a lot of times there's a good example question for symmetrical components, actually, when you have a phase open on a Y load, I believe. Aaron said, if connected to the neutral, would it be 480 divided by the square root of 3? Yep, exactly. Who here, by a show of hands in the chat, who here works in the MEP industry or with commercial voltages, or who here works, you're either speccing panels or you're dealing with like a 208 3-phase panel? Who? Eric said I do, Carlos said I do, me, Aaron, Zach Shepard, good. This is the easiest way that I remember this stuff. Rel said, good, a lot of you guys. Let's look at this. We've got a 3-phase panel, okay? So we could even go one further and say, we've got, someone give me, okay, you guys that just said me, what's a higher voltage at the switchgear level that you guys are used to seeing? Not a lighting panel, not 480. What's a voltage a little higher than 480 that you might see in an electrical room from time to time? 5 kV, 4160, 2400, 2400. Okay, let's pick on 2400 was a common one. Let's pick on 2400. So we've got a 2400 switch gear, right? 3-phase. And that feeds we'll just draw the one line, right? So we've got, depending on like your standards or how your drawings are drawn, it looks like this. You've got your transformer, and we'll even throw in a breaker. There we go. So that transformer feeds, we'll say this is an MLO, right? For you guys that work on this stuff. And this is a 208 volt 3-phase panel. And this is, I don't know what, 75 kVA transformer, 3-phase, 2400 to 208, 120. How about that? Is everyone okay with that? I get in the habit of actually drawing that, but I think most of the time they actually use the dash to indicate the primary and secondary. So, okay, who can tell me what is the difference between this voltage and what is the difference between that voltage? Easy, right? While you guys are telling me, I'm going to go ahead and finish drawing my little panel down here. Phase and line voltage, exactly. Okay. So this 3-phase panel, it's going to be right here. Here's my neutral bar. We're going to ignore grounding for the sake of this problem, right? Here's my A, B, and C. This is my 3-phase 208 volt panel. Now, okay, you guys, how about give me what's a common 3-phase 208 load that you see? Give me a common 3-phase 208 load. While you guys are telling me, I'm going to go ahead and draw my breakers. So UPS, AC, exhaust fan. Let's go with exhaust fan. I like that one. All right. So here's my 3-phase breaker. Let's say that exhaust fan is, let's say it's pretty big, 55 amp breaker. Really big, huge building exhaust fan. How about that? So that comes out and goes to my fan circuit, right? It goes directly to that motor for my exhaust fan. Big ass fan. Yeah, I agree, Carlos. And then this is our 3-pole breaker, right? 3-pole breaker, tandem breaker, whatever you want to call it. Essentially, all three operate together. Now, what's my line volt? How about this? I'm not going to say line or phase. What's my exhaust fan voltage? Looking for a number value. What's my exhaust fan voltage? 208, right? Notice we don't really have to specify 3-phase or line to line because it's a 3-phase exhaust fan, right? So we're going to give the rate. If you look at the nameplate on that exhaust fan, if it didn't use a neutral for any kind of internal control circuit, if it was just on off by the breaker, right? That nameplate is going to tell you, hey, give me 208 volts. Now, how about this? Let's do B to C. What's a common I'm not going to say single phase or 3-phase yet. Let's just say a 2-pole breaker from a 208 panel. What's another common load you see? Dryer. Perfect. I'll take that. So then this one goes to the motor. We'll say it feeds the motor on our dryer. Okay. What's my voltage? Careful, Omar, and careful, Mary. What is my voltage? 208, isn't it? 208 single phase. So Mary and Omar, I'm going to pick on you guys for just 1 second. Look at this, right? I've got a motor is fed across 2 phases of a 3-phase source. Isn't that just like this? Couldn't this be our dryer? And our line to line would be 208, you see? Now, so that's a 2-pole, right? 2-pole breaker. Now, last example. What if, I have to extend these down a bit. Now I've got one breaker. We'll say off our A phase. Let's say this is just, it's going to feed a lighting circuit. And then the return from that lighting circuit comes all the way back and feeds our neutral. What's my voltage? Yeah, 120. Single phase. So when you hear things like a single phase load is connected across a three-phase source, it happens all the time, right? We're so used to thinking in terms of delta, Y, and stuff like that we forget what's the point of all this is we're trying to get to feeding power to a panel or a motor control center or something like that, right? And when we're in that panel, we just have bus bar we're connected to. And really, delta Y doesn't matter, right? Delta Y is just the winding configuration. We still have, if our panel is Y fed or delta fed, the only difference, we're going to have a neutral, so this will have to be a Y fed. So there is a difference, but essentially, when we get to this level, it all depends on, are we connecting across two phases? Are we connecting across three phases? Or are we connecting across one phase in a neutral? Aaron asks, can't single phase mean phase to phase and phase to neutral? Yep. You will see this as, here's 208 volt single phase is what they call that. Even though it's across two phases, it's still a single phase load. Kahina asks, what is V primary value? Is it 2400 volts? So V primary on this transformer right here, I'm assuming would be, 2400 volts. So that transformer is our one line. That transformer is not pictured here. So all we're showing right here is just our panel. So this panel right here is going to be this guy right here. Kahina said, Carlos said, don't forget the crazy leg. Yeah, delta crazy leg. Crazy leg, high leg, all sorts of names. That's fun, huh? Troubleshooting that stuff late at night. Kahina asked, so 208, is that secondary? Yes, Kahina. So how about this? This transformer right here, let's draw it out. Let's draw it like we're used to seeing it. So this would be what? This would be a 75 kVA. And essentially it would be a 2400 to 208. I personally use the dash. Sometimes you'll see, I use the slash or the backslash. Sometimes you'll see the dash. I'm not sure what the real standard is or if there is one, but I know looking at nameplates, you usually see the slash when you're indicating the difference between the single phase secondary and the three phase secondary. All right. Any questions? Any questions on this stuff? Everyone feel good? Everyone feels like they won't be confused next time they get asked to find the current or find the, how about this? What if we had to find the power? Same thing, right? As long as we're using as long as we solve for the current or we're squaring the line voltage in this case. Keenan said, got it. Thank you. Good. So everyone feeling comfortable? Everyone is not going to shy away when they see these problems? All right. Well, I think that's the last one for tonight. Now, I put this one at the end because I wasn't sure if we're going to have time to get to it, and we have talked about it before, but it's come up from more than one people in emails. So let's say three-phase fault current analysis. Just go ahead, give me some complex impedances. Let's make them all lag, and give me single digits so it's not too crazy. Go ahead, just type it down in the chat. I'm going to pick the first three that come out. Okay, first one is 2 plus J3. Next is 0 plus J5, sure. And next is 20, okay. 20 ohms, perfect. Someone give me the impedance of our source. Again, we're not going to worry about realistic numbers. We're just going to pick some numbers for the sake of the example. Someone give me a complex impedance. So give me both real and imaginary for my source. And give it to me in ohms. Okay, 4 plus J5. Now, if we want to calculate this short circuit current, how do we do that? Don't forget, this is a 3-phase transmission line. I bet I'm going to catch about half of you with this, which is why we're going to go over this since we've gone over it before. But someone let me know in the chat. Go ahead. Let's pretend that I'll even go one step further. Let's say Z equals to all of it, right? Z is our equivalent, 4 plus J5, 2 plus J3, 0 plus J5, and 20 ohms. How do we solve for I? Good. Good, Jonathan. Good, Kahina. Good. So for those of you that can't see, if you're going to be watching this later, last time we talked about this is, even though it says fault current analysis, it's really just what? This is really just a simple circuit analysis problem. At least this. If we want to find short circuit, we're really just finding I. Where you need to be careful is if you say, okay, well, circuit analysis, easy, straight line, 4 impedances, they're all in series. So all I got to do to find I is take my voltage, divide by my total impedance, right? So all I'm going to do is, let's say this was a 13.8 kV line system. So all I got to do is take my 13.8 kV divided by my equivalent impedance. Careful. This, and I'm going to cross this out. Who can tell me why that's going to give us the wrong answer? Who can tell me why? Aaron said because all contribute. Not quite what I'm looking for. Aaron said, or Carlos said phase shift. Not quite what I'm looking for either. Let's say we're just looking for the magnitude. So that 13.8 kV, and I missed a K, is our magnitude. And we're just going to use our equivalent impedance magnitude. All right, seeing lots of answers in the chat. Yep, 3-phase, not voltage at the fault. Impedance is given per phase. Yes, and I want to point out, Alex asked it, but impedance is always given per phase. So impedance, unless you have a problem that says, that specifically states otherwise, impedance is going to always be per phase, which is why we need those phase voltage values. Carlos said you need the phase voltage. Yep. Omar said we need to find one phase. I think that meant I short circuit values. Yeah, so exactly. What if we took this? So this is a one-line diagram, right? When we want to solve for current, couldn't we take this and draw a single phase equivalent circuit? Here's our generator. Here's the first impedance. Here's my second impedance. Here's my third impedance. Now I can solve for I, but I got to use what? I got to use that phase voltage. Careful with this. It's going to catch you off guard because it looks so simple. Always be asking yourself, am I looking at a 3-phase system? Am I looking at a single-phase system? Do I need to draw a single-phase equivalent circuit? Ask yourself. If you're not sure, draw it out. Once you draw it out, typically the relationships will jump out at you. Rel said, wait, so how do you solve 220 square root over Z? Rel, if you can retype that, I'm having a hard time following you. Sarb said, what if the system is a delta? Great question. Who can answer me? Who can help me answer Sarab in the chat? What if this was a delta source? So remember, it's not the system, right? It's the source or the load. It's how that's connected, right? These lines in between, those are just three physically separated conductors or bundles, right? It's how they're connected in between is where delta and Y comes into play. But a good question, what if it was a delta? Keena said the same since his line current. Yeah. We would model, and this goes back to I think it was the second live class we did. We did three-phase power circuits. Even if it's a delta source, we can model it as a Y source. Of course, it doesn't exist in real life, but we can use the relationships on paper to say, if this was a Y source, what would my phase magnitude voltage, what would the magnitude of my phase voltage be? What would the angle of my phase voltage be? If I had that information, then I could solve for I, and that I would be the same I, it'd be my line current if it was a delta source. So it doesn't matter, delta or Y. Any other questions? Aaron said, I got lost at 220 kV T line. Burl said, so V is divided by square root 3, which is 220. No, rel. So in this problem, we said it was 13.8 kV. So in this problem, V would be, how about this? Our phase voltage magnitude would be 13.8 kV, 13.8 divided by square root 3. So that would be the magnitude right here on our single phase equivalent circuit. Saurabh said, wait, but would V line be the same as V phase? No. Let's do this. Saurabh said, in this case, hence voltage will not be divided by square root of 3. False. Voltage will still be divided by square root of 3. To find the line current, voltage will still be divided by square root of 3. Carlos, for the delta, don't you need delta divided by 3 for Carlos? Yes. However, remember that these are not three-phase loads. These are our line impedance. So line impedance is going to be on the line. Let's look at this. I've been meaning to draw this out for a while because who really knows the difference between line current, phase current, and line voltage and phase voltage? So we understand them mathematically, more or less, right? But let's look at this. Shamil said, so I short circuit is always per line. Would we never have to add three-phase currents for a fault? No, Shamil, you would never want to multiply your line current by 3 because remember, this I right here, our line current is what? That's the individual line current on each of the 3 phases. Let's draw this. I think this is going to be an eye-opener for some of you. So here's a delta. Okay. And here is a Y. Shamil asked, yes, the current is the same, but the total current would be 3 times the 3-phase current. No, be very careful, Shamil. When we give current values, they are always per phase. The only time that 3 multiplier comes in is power. Your total 3-phase power is a total power in the system. Line current is the individual line current per phase, and it's always going to be equal for balanced system. So be very careful. That'll get you in trouble. Watch this. I think this is going to help quite a bit of you. All right. I'm going to zoom out just a little bit, and let's go ahead and make some room. And I bet 1 or 2 of you probably know exactly where I'm going with this too. All right. Who can tell me, let's pick on our Y first. Y tends to be a little more intuitive. On this Y right here, where's my phase current on my Y? Where's my phase current? Where does it start? Where does it end? Line to neutral, or if this is a source, let's be more specific. If this is a source, we typically show it from neutral to the line, right? So here's my, let's say A, B, and C. Here's A, here's B, here's C. So all of these are my phase currents, correct? These are my phase currents of my source. Now, this is why I'm not a fan of when people just say this for Y. They say, oh, Y system, phase current equals line current. This is true, but this gives a very false understanding of what the difference is. When you say phase current, you're actually talking about the source. When you say line current, you're talking about the three conductors, the individual transmission lines, or the individual bus bars that connect your source to whatever it's going to, or vice versa for a load. So look at this. These are our phase currents. Now let's go ahead and let's connect our lines to our source. So A line goes to our A phase of our Y. B line goes to our B phase of our B source. And C line goes from our C line to our C source. Okay. Where's my A line, my B line, and my C line? Where do they exist? Right here, right? Let's draw them right on top. Here's ILA. Here's my B line current. Here's my C line current, right? When we say for a Y that our phase current equals the line current, what they're saying is the way the Y connects to a three-phase system, according to nodal analysis, right? Look, there's nothing else leaving or escaping this node. So I phase has to equal to what? I line. What about for my delta? So let's say this is A line, here's B line, C line. Here's our line currents, right? Really easy, no tricks there. Now, here's our phase currents, right? If it's plus to minus. Now we connect I line to the A phase of our delta. We connect our B line to our B phase of our delta. And we connect our C line to our C phase of our delta. How do I go from the phase current of my source to my line? Easy. Line equals square root of 3 times my source phase current. Now, what about for voltages? So let's talk about the voltage differences. Once you work this out a couple of times, I think you're not going to get fooled by it again. So when they say that they're equaling, it's because of the relationships of how the delta is connected to a three-phase system, or how a Y is connected to a three-phase system. You'll notice my lines, they don't change, right? They're just three separate conductors carrying a current. Lines don't care if it's delta or Y. It's the delta or Y that's changing. That configuration is what changes our relationships. All right, let's look at our voltages. Who can tell me where is my phase voltage of my source? Everyone good with that? It's going to be from top to the neutral. They can say, they say, okay, what's the three-phase line value of the source? But really, what's happening here? We have three separate sources tied together at the center, and all three of them are 120 degrees out of phase, right? That's what's really going on here. What's my line voltage if I were to measure across my line? So here's plus VL minus, right? Here's plus VL minus. All right, let's go A line, A phase. Let's go B line, B phase. Let's go C line, C phase. So if I want to measure, right, again, here's my phase voltage of my source. If I want to find out what my line voltage is, how do I get from my source phase voltage, how do I get to this equivalent line voltage? Multiply by the square root of 3. When we're talking about line voltage and line current, we're actually talking about what's either the voltage across two lines or what's the current flowing through down one of them. We can relate what it is to what our phase source is, right? So even though three-phase transformer, we're still going to give it. So if we say, 4160 to 480, yes, these are our three-phase line-to-line voltages, because what do we care about, right? We're using that Y source to transmit a line-to-line voltage of what we need. Now, what about our delta? So remember, delta, our phase voltage and our line voltages are the same. They're not saying the phase voltage of the delta and the line voltage of the delta. Yes, they are when you measure it, but really you're comparing the individual phases of the delta to the line. So let's go A line, A phase, B line, B phase, C line, C phase. Great. Here's my line voltage, plus VL minus, right? That would be plus A to B. Here's my phase voltage. Across one phase, I got VA to B minus. So since these are the two same points, right, across 2 points, VL equals V phase. Does everyone see that's why these relationships are the way they are? When we use the term line, we're actually talking about these guys right here. So going back up, the reason why we had to use the square root of 3 in this example for this generator is because if I want to find, I passed, didn't I? If I want to find this current off of impedance, I have to use my phase voltage. Let's go to this too. What about line impedance? Here's my line impedance right here. If they say a line impedance of, so ZL equals 2 plus J5 ohms, that means this impedance right here is 2 plus J5. That means this impedance right here is 2 plus J5. And that means that this impedance right here is 2 plus J5 for a balanced system. So you never need to multiply the square root of 3 by your I, right? Now, let me preface that by saying some power formulas, right, is what? 3 times our single phase. So we would have 3 times our V magnitudes and my I magnitude times what? Power factor. So yes, of course, you're going to see a 3 with an I from time to time, depending if you're working 3-phase and single-phase formulas. But they're never going to say what's the total line current. You're never going to be expected to sum up the 3 line currents if you're just expressing amps. Shamil said that has definitely helped me a lot. Makes sense. Yeah, this stuff, it becomes much more. You start to see for how simple it really is, and it's funny that it can be very complicated, and it seems complicated on the surface, but when you drill down to the diagrams and the formulas, everything, it's so simple that it gets tricky. It's really surprising, actually. All right. Any other questions? We're getting close here. I'll take those are actually I got through all the examples I want to get through. So we'll do a couple of more questions, maybe for another 15 or 20 minutes, and then we'll call it a night. Any other questions? Shamil said, so I'm sorry, Swarb. Swarb said, so once again, why do we divide voltage by the square root of 3 in the previous problem if the source is a delta? Okay. Swarb. Let's use this right here. I have a line impedance, okay? That line impedance is equal to some value in ohms, and they're all equal. If I want to solve for IL, if I use my voltage from here to here, it's not going to give us the right answer because this voltage reference, we're taking this in account from here to here, okay? But this isn't to ground, right? That's not to a return or anything like that. When you look at the Y system, this neutral point for a single phase load, that's a return. This point is your common reference for all three sources. So I'm trying to think of a better way to explain this. Essentially, when we transform the delta to the Y, we're essentially modeling it on paper, right? Of course, it's a delta source. It's not going to physically change, but we're doing that. We're using the math of how it works out to solve for our IL. All right, any other questions? Let me see. I'm scrolling up so I can get them all. Alex said, if it's a delta, why do we need to divide by the square root of 3? I would say, so Alex and Swarab, I want to say it's the live class number 2. The recording is up and the notes are posted too. That's one of the things we covered in the very beginning, and we talk about that quite a bit. I would say if you take some time, I think it'll clear a lot up. We went really into detail on that. I wish I had a better way to explain it. I'm sure something will come to me after the fact that will make it much more clear. Something does, I'll send you a note. How about this? Let's look at this delta again. What about our IL equals square root 3 times our phase voltage? I'm trying to think of how I can say this in terms of our line current or phase current that will make sense. Again, let me see. I'm going to take some more questions. If I come up with a better way, I'll come back to you. But if you watch that other webinar, I guarantee it'll click for you. Omar said, Zach, I have a question for the auto transformer. Is N2 stacked on top of N1 and vice versa? Should be the same calculation. Okay, great question. And that's one we can solve really quickly. So how about this, Omar? Let's pretend we have an auto transformer here. Okay. And let's say we have an auto transformer that looks like this. All right, Omar, I'm looking for you in the chat because you asked this one. Let's say we've got a number of turns of, this is 10 turns and this is 5 turns. What is my transformer ratio? What is my N1 to N2, which is equal to the same ratio as our primary to our secondary, right? If this is our primary and this is our secondary. It would be what? 15 to 5. Because on this side, we've got 5 plus 10 gives our 15. That's what our primary is seeing. And our secondary is only, it'd be 15 to 10, wouldn't it? There we go, 15 to 10. Because now our secondary is only seeing 10. Let's try it again. Let's look at this one. So here's our primary voltage, and we flipped it around, so now it's a step up. Here's our secondary voltage. Let's say this is 3 and this is 7. So we have N1 to N2. Looking from the primary, we have 3 turns. Looking from our secondary, we have what? 7 plus 3 turns. So that's going to be 3 to 10. You see that? All right. Any other questions? I'll take a few more, and then we're going to cut it off. What else? Michael, you're welcome. Thanks for reaching out. Appreciate it. Keena said, do you mind going quickly through relays? Maybe a small introduction. Sure. We'll cover that, and then I'm going to cut it off after that. So let's talk about relays, and then we'll wrap up from there. So relays are essentially what? A relay is an electrically controlled switch. Let's look at the light switch on your wall, right? You've got a hot and neutral flowing through it that flows to your light switch. If I've got a voltage source on this switch, I can close it to energize it, or I can open it, right? A relay, if you've ever seen them in person, there's like ice cube relays, motor starter relays, or all sorts of relays. But essentially, I'm going to draw it like this. So this right here is a spring. And these right here are contacts. We use relays to control the power to circuits, mostly for safety or for remote reasons. Say I've got a motor, right? Let's say this is all 3-phase system, and this is 480 volts. Do I want to be switching 480 volts? No, right? Turning on a 120 volt light switch, no big deal. What about if this was, say, 4160? Would you want to physically switch that? No, right? Because the voltage is so high, you're going to have an arc, right? Even in normal conditions, when you make or break that voltage, you're going to have an arc, unless you're in a vacuum tube or anything like that. But so what it really does is you use a much smaller voltage to control it. So let's look at this. This is 120 volts, no different than flipping a light switch. And this is a push button station. An operator or a technician can push this button closed. It'll energize this coil. It makes an electromagnet that attracts these contacts, closes that switch, and puts our 3-phase power to our motor, and our motor starts. When we open that switch, we kill the electromagnet. The springs inside here push our relay contacts back open, and it interrupts our flow of power to our motor. So essentially it's for 2 reasons: for safety. And what if you've ever been to an industrial facility or a place where there's a lot of different loads, what if I had 100 motors? Without a relay, someone would have to run around and physically turn on each and every motor by hand. Well, here I could have all of my buttons located in the same room in like a relay control panel, which, like, even a good example, if you've ever been to like the airport at the tarmac, you usually see them. But essentially a bunch of push stations, all on one panel. You can have a run, jog, stop button. You can have a 3-position handoff auto switch. You can have these all in close proximity, and your motors can all be hundreds of feet away in all sorts of different directions. So it prevents us from having to physically be responsible for switching the higher voltage that the load needs to operate. So it removes us from danger, right? It takes us out of the danger. And it's much more efficient. One operator, one technician could sit in front of a relay panel and push all those buttons, start up all those motors, versus running around, right? Because you can have hundreds and hundreds of feet of 120 volt control power. It doesn't matter. Work all day. You can also go one step further. PLC, you have a contact, right? You have your 120 volt coming in. That's going out. Maybe your PLC is now going to your relay. And your PLC acts essentially like a relay, except you have a program. When the program is satisfied, it closes this contact, which flows power from your hot through your PLC contact output to your relay, energizes that coil, brings your contacts down, and passes through your higher voltage to your load. All right, it's about 11:17. Hope you guys got a bunch out of this. I am working on the power electronics module. I'm hoping to have that. If I can get it done tonight, I'm going to try. It's going to be kind of tough. It's late here on the East Coast, but we did spend a lot of good time here tonight. That module should be done by tomorrow. And I'm going to go ahead and get this recording up and posted tonight along with the notes. That way, tomorrow when you guys want to watch it, it'll be ready for you first thing. So thank you, everyone. Enjoyed it tremendously. Hope you got a lot of value out of it. And just remember, keep your head up. We're getting close, right? We're going to have one more live class. If you're starting to doubt yourself, if you think you haven't studied enough, now is definitely the time to put in the extra effort, right? Now is not the time to let up, because I want each and every one of you to do what? I want each and every one of you to have that successful student mindset. And I know all of you guys are going to do just fine. So thank you, everyone. Thanks for all the thank yous. I appreciate it. And we'll see you next week. Bye-bye.